British steam locomotives were some of the most beautiful machines ever built. Sleek, powerful, record-breaking. The A4 Mallard hit 126 miles per hour and still holds the world speed record for steam. These engines hauled prestige expresses like the Flying Scotsman service, the Coronation, and the Cheltenham Flyer. They were the pride of a nation that invented the railway itself. But here is the brutal truth. Drop one of those magnificent British engines onto an American railroad in the 1950s, and it would struggle badly. Not in a week, not even in a day. Within hours, crews would realize they had brought a precision instrument to a bare-knuckle brawl. Two countries built extraordinary locomotives for environments that could not have been more different, and the moment you compare them side by side, the incompatibility becomes obvious. Let's start with the terrain, because that's where this story really begins. Britain is small and relatively flat. The entire country is about the size of Oregon. Many mainline railways were built with gradients no steeper than about 1 in 100, that is 1%. Even the infamous Lickey Incline, Britain's steepest sustained mainline grade, only hits 2.65% for 2 miles. British engineers considered that extreme and stationed helper locomotives there permanently. Now, let's talk about America. Saluda grade in North Carolina averaged 4.24% over 2.5 miles. The steepest sections reached 4.9%, and that sustained punishment lasted for miles. The climb from Ogden through Weber and Echo Canyons to the summit at Wasatch followed Union Pacific's long 1.14% ruling grade, a steady ascent of nearly 2,000 feet into the Wasatch Range. Cajun Pass out of Los Angeles had 3% sustained grades that went on and on. These were not rare exceptions. This was normal for Western American railroading. British locomotives like Mallard were designed with 80-inch driving wheels, massive drivers for high speed on gentle terrain. Put those same wheels on a steep American grade, and physics becomes your enemy. Large drivers mean less adhesion, which means constant wheel slip when you are trying to haul tonnage uphill. The locomotive that set speed records on the East Coast Main Line would be spinning its wheels helplessly on Sherman Hill. American locomotives were built completely differently. The Union Pacific Big Boy had 68-inch drivers. The C&O Allegheny had 67-inch drivers. They sacrificed top speed for grip and pulling power because American railroads needed to haul 4,000-ton freight trains over mountain ranges, not sprint passenger trains across the English countryside. And the weight difference tells you everything you need to know about the scale of American operations. A fully loaded A4 Mallard weighed about 165 tons in total. Impressive for Britain. The Big Boy was about 1.2 million pounds, roughly 600 tons. The Allegheny tipped the scales at close to 600 tons as well. These were not just bigger locomotives, they were fundamentally different machines built for fundamentally different work. Because here is what American railroads demanded. Move massive tonnage over brutal terrain with whatever fuel you could get, and do not come back to the shop for hundreds of miles. Let's talk about water, because this is where British precision engineering hits American reality like a brick wall. Mallard's tender carried about 5,000 gallons of water. That was fine in Britain, where the country is covered in a dense network of water stops every 50 to 100 miles. The Big Boy carried around 25,000 gallons, roughly 5 times more water than Mallard could take with it. Why? Because you might cross 100 miles of Wyoming desert without seeing a water tower, or climb through Nevada mountains where there is nothing but sagebrush and empty sky. British locomotives would be dead in the water, literally, before they had gone a fraction of the distance American operations required. The Allegheny carried 25,000 gallons too. These enormous tenders were not showing off. They were survival equipment. Then there is the loading gauge, and this is where British steam physically could not compete, even if you wanted it to. British railways were built in the Victorian era with very tight clearances. The loading gauge, the maximum size a train can be, was roughly 13 feet high and around 9 feet wide, locked in by thousands of bridges, tunnels, and platforms built in the 1800s. American clearances ran closer to 15 feet high and about 10 feet wide as standard, with many Western routes even more generous. That extra space was not cosmetic. It meant bigger boilers producing more steam, bigger fireboxes burning more coal, more power, more capacity, more everything. A British locomotive could not be built large enough to match American freight demands without crashing into every bridge and tunnel on the line. Even the track structure was different. British rails typically weighed 113 pounds per yard, with a maximum axle load of about 25.4 tons. American heavy freight routes used rail sections up to 141 pounds per yard and were designed to handle axle loads in the range of 30 to 36 tons. The entire infrastructure was engineered for punishment that would destroy British track. And then there is coal, where the difference in philosophy becomes crystal clear. Welsh steam coal was exceptionally high quality, typically around 13,000 to 13,500 BTU per pound, with some seams testing even higher. British locomotives were precisely tuned for this premium fuel. Skilled firemen knew exactly how to work it for maximum efficiency. It was engineering at its finest, optimized for perfection. American coal was all over the map. Powder River Basin sub-bituminous coal averaged about 8,500 BTU per pound. Eastern Appalachian bituminous coal was around 12,500 BTU per pound and had higher sulfur content. Illinois coal fell somewhere in between. American locomotives had to burn whatever was available wherever they were running, and the coal quality could vary wildly even within the same state. So American engineers built massive fireboxes with robust grate systems that could handle anything from premium coal to borderline lignite. British engines tuned for Welsh coal would struggle badly on inconsistent American fuel, causing poor steaming, excessive smoke, and constant firing problems. Maintenance tells the final part of the story. British railways operated with depot networks everywhere, tight maintenance schedules, regular inspections. Locomotives were serviced frequently because the infrastructure supported that level of precision care. You might run a locomotive 300 miles across empty country before reaching a major maintenance facility. Break down in the middle of Wyoming, and you are blocking the main line for hours with no help coming. American steam was designed to take abuse and keep running. Simple, rugged, and repairable in the field with basic tools. British precision versus American brutality. Two philosophies for two completely different worlds. So imagine actually trying this. A Mallard on the Union Pacific Main Line would be a catastrophe, slipping drivers on every serious grade, running out of water far too quickly, struggling with Western coal, and requiring constant maintenance it could not get. While next to it, a big boy hauls 4,000 tons up Sherman Hill without breaking a sweat. And the reverse? A big boy in Britain would smash through loading gauge restrictions, crush Victorian-era track with its massive axle loads, and be complete overkill for 300-ton passenger trains on comparatively gentle routes. Neither country built bad locomotives. They built exactly the right locomotives for their world. Britain needed speed and efficiency over shorter distances, with premium fuel and comprehensive support networks. They created masterpieces like the A4s, the Coronation class, the Kings. America needed raw power over punishing terrain with inconsistent fuel and minimal support. They built monsters like the Big Boy, the Allegheny, the Yellowstone. British steam would have struggled brutally in America, not because it lacked quality, but because it was engineered for a different reality. And that is the real fascination here. Great engineering is not universal. It is specific. A machine is only as perfect as the world it is built for.